Good morning. Yes. Okay, in the previous class, we discussed the eigenvalues and eigenvectors of 2 by 2 matrix. So today we move to 3 by 3 matrix to determine the eigenvalues and eigenvectors of this given matrix. So the process is the same, like the one we did for 2 by 2. It's just that this one is just long and more involved, but the process is the same. So basically I've already solved this one. I'll just explain the concept. Okay. So you can clearly see here I wrote eigenvalue problem and eigenvalue. I'm determining the eigenvalues. So the first step that you do, you use the equation, this one, the determinant, the characteristic equation, the determinant of A minus lambda I equals to 0. So this means you give this matrix a name. You can just call it A or anything. So this is how I achieve the first step here. So usually you can say that basically our lambda will subtract on the diagonal. So I think now you are familiar with that. And the rest will remain the same. Okay. And the rest will remain the same. So immediately after that, you determine the determinant. You know how you hide. So this is how I'll just show for the first one. This is how you hide. So you have 1 minus lambda. This 1 minus lambda, 2 and 5 minus lambda. And you multiply it by minus 2 minus lambda plus 4. So this plus 4 comes from the signs. We have positive, negative, positive, negative, positive, negative, positive, negative, positive. So you can clearly see that this middle sign is negative and our 4 here is negative. So negative multiplied by positive gives me positive. Okay. And then you hide again. This time you hide the middle term, the middle column. You hide the middle column and the top row. So you have minus 2 and 4, 2, 5 minus lambda. So that's how I got those ones. Okay. And then the last one is, you can see here, this is positive. It's positive 2. And then you hide the last column and the top row. So you end up with minus 2, 4, 1 minus lambda, and 2. So the determinant is the same way we have been doing it. Choma, switch off your mic. Okay, so the determinant is the same way that we have been calculating. It is just that this one is just long because it involves those lambdas. So I managed to sit down and do it. So this is the process you have to go through it. You multiply the way we have been doing. So the equation that you use is AD minus BC. So you multiply the diagonal. AD is the diagonal. So you multiply the diagonal minus the non-diagonal. The 2 multiplied by 2. So this is exactly what I did here. Multiplied by this pi for 2 minus lambda here, plus 4. You do the same for the rest. And after that, you just multiply and simplify. I end up with this equation here. The reason I've done it is because it's very long. This one problem can take maybe 2 pages to determine the eigenvectors. So I end up with this equation. So instead of using a vector theorem and remainder theorem, I just used my calculator. So I went to mode and then I choose equation number 5. After number 5, I choose 4. Then from there, I just substitute the coefficient, which is -1, 4, 27, and -19. And then from there, you can see that our eigenvectors are -5, 6, and 3. Now, immediately after achieving the eigenvectors, what do? You substitute, we say for lambda equals to -5, you solve. For lambda equals to 6, you solve. For lambda equals to 3, you solve. So I have managed to solve all 3. Okay, so the first one is when for lambda equals to -5. So if I go back just to show you, on the diagonal, you see the diagonal is 3. That's where the change is located. 3, 6, and 10. So we are substituting -5. Let's see. We're going to our original matrix. So here we have -2 -5. Let's see. So it's going to be -2 plus 5. So the answer is 3 here. 1 minus -5, so this will give you 6. 5 minus -5, this will give you 10. So that's how I got those values. The changes on the diagonal, 3, 6, and 10. Then immediately after that, what do? Immediately after that, now I'm going to use, because this is 3 by 3 matrix, it's not direct like the 2 by 2 matrix. So you can see the only way I can solve this problem is to use what we call Gaussian elimination. So I'm using Gaussian elimination to determine the eigenvectors. So now, in the previous classes, I said you should make the leading entry 1. So, but when I look at this one, it's going to take long to make. I'm actually trying to avoid fractions. I usually make mistakes with fractions. So if I divide row 1 by 3, I'll end up with -4/3, 2/3. So instead of doing that, to avoid that, what I do is this. I use the method that we're using in high school for elimination. I'll just explain it here, what I did today. I multiplied equation 1 by 2. This means it's going to give me 6 minus 8 and what? And 4. And I multiply equation 2 by 3. So this is -6 plus, even if I don't put plus, it's okay. So 6 multiplied by 3, it will be 18. And then this will be 6. So from there, I subtract. This will give me 0. This one will give, this is positive. This one will give me 10. This one will give me 10. So that's how I arrive at this equation here. Equation number 2. Okay. Now I have achieved my goal of making this guy 0. We move to the next one. Now you want to make also 4 0. So what do? You want to make 4 0. So you apply the same thing that I did on that one. You multiply. I'll explain it again here. You multiply equation 1 by -4 and multiply equation 3 by 3. So it's going to be 12 minus, we're multiplying by equation 1 by 4. So it's 12 minus 16 plus 8 here. And the last one, this one multiplied by 3, so it's going to be, is it negative? This one is -4, so it's going to be -12 here plus 12 minus 8, okay? So this one here is going to be multiplied by 3. This is 12 multiplied by 3 plus 6. The last one, which one are we multiplying? By 3. I'm getting confused now. Equation 3 multiplied by 3, let's see. I have multiplied the first term. It gives me 12. This one gives me what? By multiplying by 3 is 6. And if you multiply 10 by 3, what do you get? Seems like something is wrong there. 30. Okay, now I get it. So this is 0. If we add these 2, it gives you 22. We add these 2, it gives you 22. So this means I'm correct. Okay, so that's how I have achieved these two equations. Now you can clearly see that I can divide equation 2 by 10. So I end up with 1 and 1 and 0. That's the first statement here. And even equation 2, I can divide it throughout by 22. Then I end up with that. Okay, so this is how I achieved. I have indicated there on the operations how I achieved that one. Now, equation 2, we multiply equation 2 by minus 1 plus equation 3, you get equation 3. So you can clearly see that we have 1 and 1, 1 and 1. So we will end up with zeros. So I have 0, 0, 0, 0. So in the previous classes, when we discussed the type of solution, we said if we have this type, we have infinitely many solutions. Now today I'm going to indicate how are we saying we have many solutions. You can let z equals to t. So because this 0 here will represent z. So z equals to t. So if z is equals to t, what is y? So we have y plus z equals to 0 on the second equation. So you substitute, where you have z, you substitute t. So y plus t is equals to 0. This means y is equals to minus t. Now on the first equation, we have 3x minus 4y plus 2z equals to 0. Now you substitute 3x minus 4 minus t plus 2t equals to 0. Now you solve this one. So you have 3x minus, so if you add these two, they give you 6t equals to 0. So this means x is equals to 6t divided by 2. So this is equals to 3t. Now, immediately after that, you can clearly see that you can take t out as a common factor. So the eigenvector, so I have also done it in detail here. So the eigenvector k1 is equals to, you can take t out as a common factor. You have minus 2, minus 1, and 1. So this means our z is 1, our y is minus 1, and our x is minus 2. So that's why we say we have infinitely many solutions. So it will depend on the type. You can choose t to be anything. It can be 0, it can be 1, it can be 10,000, it can be so. So we have many solutions. That's where the term comes from. Infinitely many solutions depending on the value of t that you substitute there. But now, because here we are dealing with eigenvectors, for simplicity, I choose t to be equals to 1. So the value for k1 that I'm going to use is this one. Like I said, for simplicity, this means you can choose anything. But to simplify our work, we choose t equals to 1. Okay? So this is how we determine the eigenvectors for this one. So remember now, because we have 3 by 3 matrix, we expect to have k1, k2, and k3. So we have just started with k1. Now we need to determine k2 and determine k3. So we used this one we used lambda equals to minus 5. The next one we might use lambda equals to 3, lambda equals to 6. Okay. So on the next equation, like I said, we substitute lambda equals to 3 on our diagonal. So our diagonal is in the first one. We substitute 3 here. So we have minus 2 minus 3. This will give us minus 5. 1 minus 3, this will be minus 2. 5 minus 3, this will be 2. So that's how we got those diagonal. Minus 5, minus 2, and 2. Now, immediately after that, we solve again using the method of Gaussian elimination. Gaussian elimination. So using Gaussian elimination, you can clearly see that here we take advantage that we have minus 2 minus 2, 2. We can divide this equation by 2. So I've divided it by 2, and then after that I interchange equation 1 and 2, which is allowed. So I moved this equation up, so I interchanged these two. I divided this one by 2 and interchange. So I have made equation 2, equation 1, and solve. So now my intention is to make minus 5 1. So I'm going to multiply row 1 by 5 and 8. So this term here will be 0. So it's 5 minus 5 is 0. I multiply the second term 1 here by 5. It's going to be 5 minus 4. This gives me 1. Plus 1 by 8. This gives me minus 3. Okay, that's how I achieved equation number 2. Its operation is this one. To the equation number 3, the operation is this one. My intention is to make 4 0. So I multiply equation 1 by minus 4 and 8. Minus 4 and 8 to this one gives me 0. Minus 4 and 8 to this one, it gives me minus 2. So it's minus 4 plus 2, it gives me minus 2. Minus 4 multiplied by minus 1, that will be 4. 4 plus 2 gives me 6. So this is how I achieved this one using the second operation. Okay, now if you look closely at equation number 3, we can divide it by 2. So if you divide this by 2, you end up with 1 and minus. I divided by negative 2 actually. If you divide by negative 2, you can see you end up with 1 minus 3 and 0. But now if you look at these two equations, they're exactly the same. So I can make equation 3 a row of zeros. So equation 2 multiplied by negative 1 plus equation 3, they give me equation 3. So I end up with equation which involve a row of zeros. So now I can let z equals to t. And if z is equals to t, it implies that y is equals to 3t. Okay. And then I substitute my y and z in equation 1 in the first one and solve. I end up with x equals to minus 2. X with x equals to minus 2. Now I write my value for k2, vector k2, and then take t as a constant. So for simplicity, again, I let t to be equals to 1. So I have minus 2, 3, and 1. So this is my k2. Now on the next step, obviously, we're going to use our last eigenvector. So again, you should check the diagonal. On the diagonal, we are using what is it? 6. So we check how 6 is going to affect this one. We have minus 2 minus 6 give us minus 8. Here we have, is it 1 minus lambda? So it gives us 6 minus 1 minus 6, which is give us minus 5, and the last one give us minus 1 there. Okay, we can go and check exactly. So we substitute 6 here. So it's minus 2 minus 6, 1 minus 6, 5 minus 6 give us minus 1. So this is how I achieved the diagonal. This one. And immediately again, you use Gaussian elimination. So you have to master this. Actually, if I can end up giving you this complicated, this long problem, especially for assignments, if I can give you another assignment, I can give you this one because you'll be working at home. But when you are writing major test, I find this to be very long to give to students. Okay, but if I want to determine the eigenvectors, I can compute the problem, and let's say that I have computed the problem. The eigenvector is equals to 3. Please determine the corresponding eigenvectors. I can do that. So this means we'll just compute for 1. That one is allowed, but instead 3 is too much. For doing 4, -5, 3, and so on is too much. I can just give you 1. Okay, so in this case, let's see how I have simplified. Let me erase what I don't need here to create space for explanation. Okay, let's go through it. Here, it seems like I assumed that now we have mastered the method. I didn't write a lot, I just did it mentally. Okay, I assumed at this point you know what's going on. Okay, again here, what do? Your aim will be to make this -2 0. How do you do that? You can multiply R1 by what? It will depend. R1, let's say you can make this R1 -4, R2 gives you R2. This one will also work. It will give you 0. So it will depend on how you manipulate. One student can multiply the top one by negative and multiply the one below by -1, the one below by 4. So it will depend. So this one will work. It will give you this 0 here. Let's see how. -8, -4, -2. Then you multiply this one by -4. So it's going to give you 8. You multiply by this one will be 20. This one will give you, is it 8? -8. Then you add these two. Is it -8? You have to check that. I can see I get 16, but I don't get this minus. Let's check again. It's my mistake. It's supposed to be -6, yeah?
No, it's supposed to be just
from row 1 is 2, so this will be -6 here. Okay, thanks. Now adding this, I end up with 0, 16. Okay. Oh, this is positive, and this one is -8. Thank you. So we end up with -6. Now I see what you explained. Okay, so this gives me -6 and 16. So that's how I got that. Now, there are a lot of steps that I have jumped in this one. So let's do those steps. The next step will be to determine this 0 here. So you must get rid of this 4. So how do you get rid of this 4? Which one can we use to get rid of that 4? Let's think about it. You can multiply this one by 2 and add to that one. So I'll write the operation. So R1 plus 2R3 gives you R3. This one will work also. So we have -8, -4, 2. So you multiply this one by 2. So this is 8. This is 4. This is -2. So let's see what you end up with. So this will give me 0. This one will give me 0. This one will give me 0. So that's how I determine the row of zeros. So it's 0, 0, 0, and K3. So this one was easy to get, okay? Now, once we have a row of zeros, what do? You let Z to be equals to T, okay? And then you substitute T on the top one. So you have 16 minus 6T equals to 0. So we make 16 equals to 6T. We divide both sides by 16. So there's Y here. We're solving for Y. Okay. There's Y, and then this is 6T. Otherwise, it doesn't make sense. So Y is equals to 3/8T. So that's how I got that one. The next one, we are solving for X. So you'll substitute Y and Z. So let's see what is there. It's -8 minus 4 plus 2. So this is X, Y, z equals to 0. So we substitute, let's say this is t minus 4, 3 over 8 t. So minus 8x equals to 0. So if you add these two, what do you get? You end up with, so it's plus 2t here, plus 2t. So I add this using calculator, I end up with minus 8x minus plus 1 over 2t equals to 0. Then working it out, I end up with minus 8x equals to 1 over 2t, and this is x is equals to 1 over 16t. Now, this simplifies to 1, 6, and 16. Okay. So the question is, how did I reach that point? Okay, let's write it in this way. K3 equals to, let's write it the way this is t, 3 over 8, 1 over 16. All of them, they contain t. So you multiply this term by, you can take t out. You multiply each term by 16. So we can multiply it by 16. If you multiply it by 16, you'll end up with 16t, and then 6t and 1 and t here. That's what I did exactly. Oh, I didn't write it properly. It's another way around. Okay, this guy here is our x, so it's supposed to be on top there. That's why I'm confused. So this is 1 over 16t, and this is t. So if you multiply everything by 16, so we are trying to simplify this expression, we end up with t, 6t, and 16t here. So you take t out as a common factor, you end up with 1, 6, and 16. This is correct. You can end up here. There's nothing wrong with that. This is just to simplify, okay? And then to move to this one, I have let t to be equals to 1, okay? That's what I did exactly. So you can see that this is quite involved, but I wanted you to experience it. So that's why I sit down and solve it. Okay, now we are done with determining the eigenvectors. We managed to determine K1, K2, and K3. So this is important. We'll come back to this problem. We are still going to use these eigenvectors to diagonalize the given matrix, but that will be a problem in the next next question. Okay, now if we go back here, we have solved this one. We have managed to determine the eigenvalues and eigenvectors. Now, we come to what we call diagonalization. So up to this point, last year in exam and major test, I've given students 2 by 2 to diagonalize. I don't know if they can give you 3 by 3, but 3 by 3 is quite involved. Yeah? When I was doing my BSc, it took me time to master this. Okay, but I'm going to go through 3 by 3 just for experience sake, so that you can just see how will you go through it, especially in assignments, if we're still going to do more assignments. So the next thing that I'm going to do, in the previous class, I did try to explain this one. So here, basically, we are looking for D. Okay. Okay, there's noise. I don't know if I have data or what. Problem. Noise. Okay. So what is the problem? Okay, I hope this resolves itself. Okay, our aim, I want to explain the method first before we go to the problem. So we want to determine D. Okay, so in this one, we solve this problem to determine the lambda. We had determined that lambda was 5 and lambda was 1 here. So D will be equals to 5 and 1, and this is 0, 0. So at the end, my solution will be this one. So how do I determine this solution? I have determined the eigenvectors for lambda, and if I still remember, it was what? Is it 3 and 1? And I determined the eigenvectors for 1. I think it was 1 and 1. I don't know, 1 and minus 1. You will check that. So I'm just trying to explain this concept. The concept, we are going to do it. So this gives you P. So P is made by K1 and K2. So we just put them side by side. Okay, then from P we determine P inverse. So P inverse will just use the determinant of, this is the determinant of P, and then here we change the diagonal, so it's going to be minus 1, 3, negative 1 and negative 1. So I'm just doing it based on this. This is not 100% correct. It will depend on what I've done here. Now immediately after that, what do you do? Now to determine D, you multiply. Okay. You multiply, I think this is wrong here. I think it's supposed to be P inverse. So P inverse A, P. I think this is the order, the correct order. So you multiply your inverse, P inverse by A, this multiplication, and then the product you multiply it with P to determine the answer. Okay. So let me show you where I have solved this one. So I'm not going to discuss how to determine this one. This we did in the previous class. So this is where we ended. We determined for lambda equals to 5, we determine it to be 1 and 1. Like I said, I was just claiming that one. And then for lambda equals to 1, we determine to be minus 1 and 3. Now, immediately after that, we determine P. My P is 1 and 1, minus 1 and 3. I determine the determinant of P, which I got to be equals to 4. I determine P inverse. So P inverse, so the inverse of P is given by that, using the determinant method. Then immediately after that, what do I do is just multiplication. Like I said, this is the correct way. I don't think that one is the correct way. I'll change that one on my notes for future. It's supposed to be P inverse multiplied by A multiplied by P. So we start with P inverse is 1 over 4. This is the inverse. From here up to here, this is my inverse, this is my A, this is my P. Now I'm going to do the multiplication for you. So this is how we multiply. 3 multiplied by 4, this gives me 12. And then we're multiplying a row by a diagonal, by a row by a column. So 1 multiplied by 3, this is 3. If you add these 2, this gives you 15. So that's how I got that 15. Then you multiply 3 by 1, it gives you 3. 1 by 2, this is plus 2, this gives me 5. So that's how I got that 5. Minus 1 multiplied by 4, this is minus 4. 1 multiplied by 3, this is plus 3, this is equals to minus 1. That's how I got minus 1. Minus 1 multiplied by 1, this is minus 1. This 1 multiplied by 2, this is plus 2, this is equals to 1. That's how I got 1. Now immediately after that, you do another multiplication. I'll just explain it here. 15 multiplied by 1. So this is 15. 5 multiplied by 1 plus 5. This gives me 20. This is 20. That's how I got that 20. And then 15 multiplied by minus 1. That is minus 15. 5 multiplied by 3. That's 15. This gives me 0. Minus 1 multiplied by 1 and 1 multiplied by 1. So it's minus 1 plus 1. This is 0. That's how I got this one. And then the last one, minus 1 multiplied by minus 1 gives me 1. 1 multiplied by 3, this is plus 3. This is equivalent to 4. So now we are going to multiply this matrix by the scalar 1 over 4. So if you multiply 20 by 1 over 4, it gives you 5. You multiply 4 by 1 over 4, it gives you 1. The remaining ones are zeros. You can see 1 over 4 times 0 is 0. So now I have managed to determine this diagonal D. So this process is called diagonalization. So one of the intelligent students can ask me, what are the conditions for a matrix to be diagonalizable, for you to be able to diagonalize that matrix? So the requirement is that the eigenvectors must be independent. So this is another part that I'm still going to teach under vector space. So you have 1 and 1, minus 1 and 3. So you can just determine the determinant of this matrix. If the determinant is not equals to 0, this method is called Roskin. So if the Roskin or the determinant is not equals to 0, then we can conclude that our given the eigenvectors that we have determined, the eigenvectors are independent. So we can clearly see that we got the value to be 4. So if they are linearly dependent, we cannot do this process. Okay, the requirement is that they must be linearly independent. So linear independency, the other way of showing that, you can just show it directly from the graph. If we were to plot these ones, let's say it's 1 and 1, and then minus 3, let's say minus 3 and 3. I think this will not be on the straight line. So if they are on the straight line, we say that they are linearly independent. And if you might find that another vector is at this point, another one is at that point, or somewhere here, or another point is at another point here. So where you cannot make a straight line, they are not in a straight line. So we say that they're linearly independent. So I'll explain this concept when we reach that point, but I wanted to highlight it here. What is the requirement for them to be diagonalizable, to be able to diagonalize these two. Okay, so that is the case. Now, if you go to our notes, immediately after this, what we have is say that this matrix that we have determined the eigenvalues for. Now they say we must diagonalize this matrix. So to diagonalize this matrix, now I'm going to follow this process that I have done here. The first thing that you must do, we have already determined the eigenvalues. We determine them to be minus 5, 6, and 3. Okay. And now what do? We must determine the eigenvectors of this matrix. So, did we determine the eigenvectors? The answer is yes, we've already done that, the eigenvectors, so I don't have to go through this process. So now, P is equals to that. It's minus 2, minus 1 and 1, minus 2, 3 and 1, 1, 6 and 16. So this is my P. Now immediately after that, you have to determine the inverse. So the inverse I have so here I use mathematical to determine it, but after sometimes this morning I decided that no, let me do it. Okay, so this is the process that you are going to follow. Here I use determinant method to determine the inverse. So you start by determining the determinant. So the determinant is not equals to 0. It means that the inverse exists. Immediately after that, you determine the cofactors. So how many cofactors do we have? There are 9. So how do you determine the cofactors? We'll need signs. So the signs positive, negative, positive, negative, positive, negative, positive, negative, positive. So you are going to use each and every. You are going to use -2, -2, 1, -1, 3, 6, 1, 1, and 16. So you start by hiding. So the first one, this is how I hide. You hide this one, the top diagonal, and the top row, and the column. So you have 3, 6, 1, and 16. And then this is here. You can see we have 3, 6, 1, and 6. That's when it's A11. A12, this is the location, A12. This was the first row and first column. Then it involves this 3, 6, 1, 16. The second one is going to be first row, second column. So you hide this one and that one. So you have -1, 1, 6, and 16. So these are the process of determining the cofactors. So here I was actually determining the cofactors. I've determined 1, 2, 3, 4, 5, 6 by hiding that. So my answers was 42, 22 -4, 33 -33, 0, -15, 11, -8. Okay, sorry for a moment. Okay, those are one of the disadvantages of working from home. So I managed to determine those cofactors. So I put them in a matrix. So these are the cofactors. Immediately after that, you transpose them. So when you transpose, you can see this column here. I have written it as a row. So it's 40, 33 minus 15. 40, 33 minus 15. You do the same with the second column and the third column. So this is what we call the adjoint matrix. Okay, now to determine the inverse. The inverse is equals to 1 over the determinant of that matrix that we have just computed there, multiplied by the adjoint of A. So this gives me the inverse. So that's how I have calculated the inverse. So let's go to 6. So now we have seen that this inverse is actually correct. We have tested that. Now to determine D. Now what remains now is multiplication. So I multiply this inverse by this matrix A. So remember this is PA and P inverse and P. So I multiply these two. So when I multiply these two, my answer for the first one is this one here. I don't know. This one is where you have to go and test your multiplication. It took me time to do this because it's a situation where I know the answer. I know the answer, but I'm not reaching the answer. I know my answer must be -5, 3, and 6. So on the diagonal. So I struggled to reach this. So when you write the test or assignment, so this will be your goal. You should know that the answer must be -5, 3, and 0. So you must have a diagonal matrix that we discussed when we started this. So I multiply. Let's just test. Maybe do I want to show that indeed this is 35 over 22. So this is how I will multiply. I have -7 over 22 multiplied by -2 plus -1 over 4 multiplied by -2 plus 5 over 44 multiplied by 4. So we must add this, multiply and add this to to check if you end up with 35 over 22. So I can clearly see that I have 14 over 22 plus 1 over 2 plus 20 over 44. And then I add this. So I end up with 35 over 22. So this is how you do it actually. To determine the second term, this is exactly what we're going to do. Minus 27 over 22 multiplied by minus 4 minus 1 over 4 multiplied by 1 plus 5 over 44 multiplied by 2. So this must give you 4 over 5. Okay, so that's how you do it. Okay, so I did it like that step by step. My answer is minus 5, 3, and 6. That's my diagonal matrix. Okay, so now I managed to diagonalize this matrix. I said this process is very long. During our time, they were giving us this type of problems to solve. Okay, but remember, you are doing engineering. You're not doing BSc in engineering or maths. So in the major test, I'll avoid giving you this, but in assignments, I can give you this. Okay, like I said, I can just test. So usually I give you 2 by 2 matrix. 2 by 2 matrix I can give you, but 3 by 3, I think it will take you a lot of time in exam to do that. Okay, so this is where this ends the diagonalization of this problem, eigenvalue problem. Any questions up to this point? Do you have any questions? Do you have any questions? Okay, if we don't have any questions, so in our next class, I'm not going to introduce, it's a big topic, so I must go and prepare it. We are going to deal with a vector space. So this is our next topic, vector space. After vector space, we deal with transformation. Remember, we did transformation for functions. So we are going to do transformation for matrix also. So after this will end our pre-calculus. So pre-calculus will end there. Pre-calculus ends after, pre-calculus will end immediately after this. So it ends there. Then after that we go to calculus. Calculus will start with limits and limits will lead us to the first principle. Then from there, first principle. From first principle, now we discussed differentiation techniques. So this is what we're going to do. So this vector space is a very big chapter also. I think transformation is not that big. So it might take us the whole week, this vector space or more. And then transformation, then that's it. Then we end, then we go to calculus. So today is going to be a short class. Actually, I'm going to end there because we said we are going to discuss only eigenvalue problem. I cannot move to vector space today. So any question? Okay, if there's no question, could you please end our class? I'm going to stop the recording. So I have the recordings. I don't know. Maybe I should ask the class rep to give me direct access to your chatting group. So I'm going to just send you all the recordings. I think we are finishing his data now. It's too much. So we send it. I'll send it directly to the group and then exit the group again. I don't like being part of the group. Students they misbehave sometimes. So that's what I've learned from last year. So I'll just maybe give me access for a few minutes and so on, upload the videos, and then that's it. Okay, bye. See you in the next class. That will be on Tuesday next week. Bye-bye.